All right, so we're going to continue our studies of functions, continuing with exponential functions. So basically, we saw that a linear function is of the form y equals mx plus b. A quadratic is of the form y equals ax squared plus bx plus c. Now, a exponential function is going to be a function of the form y equals c times a to the x, where a is positive and it's not 1. Why is it not 1? Because 1 to any power is just going to give you 1, so that's not interesting. And c is called the initial value of the function. And notice that c is actually the y-intercept, because when x is 0, that's how we find the y-intercept. When x is 0, you'll get that y equals c times a to the 0, but a to the 0 is 1, so y equals c is the y-intercept. The number a is called the growth or decay factor. So if a is a number greater than 1, then we have a growth function. And if a is a number between 0 and 1, then we have a decay function. All right, so given this following example, y equals 25 times 1.05 to the x, determine the initial amount and the growth factor. Well, just notice that y equals c times a to the x. So c must be 25, and a, since it's a number greater than 1, a is 1.05, and it's growth. Guys, when we multiply by a number greater than 1.5, that means a growth. So if you multiply 25 times 1.05, you see it's growing. The 25 becomes 26.25. If you multiply a number by a number less than 1, like 0.8, it's going to be decay. Okay, it goes from 25 to 20. All right, write the equation. Number 2, write the equation of the exponential growth function in the form y equals c times a to the x, where the initial population is 320. So instead of c, I'm going to have 320. And the growth factor is 5/3. So 5/3 for a and then to the x. Is this growth or decay? Well, it says it's growth. Basically because 5/3, if you put 5/3 in your calculator, you'll see that that's a fraction which is greater than 1. All right, now number 3, write the equation of the exponential growth function where the initial population is 12. So we will have y equals 12 triples. The population triples during each time period. So a is going to be 3 because it triples. All right, so after x equals 1, it will be 12 times 3, which represents that it's tripling. All right, the population of San Jose during the years 1990 to 1996 can be modeled by this equation. Yeah, I'm not done. Where t is the number of years since 1990. So let's answer these questions. What does the model give us the population in 1990? Well, in 1990, that means when, at the beginning, right? So when t is 0. So that's just the initial population. That's our c. So population in 1990 is 782,224. What was the growth factor? The growth factor is 1.0117. We're just reading this off of the equation. Another example, the pressure in pounds per square inch in a tire with a leak can be modeled by this. After t minutes, what does the model give us the initial tire pressure? Well, the initial tire pressure is 30. You just read it off of here. This is the initial tire pressure. So it will be 30. What does the model predict the tire pressure will be after 5 minutes? So we're interested in the pressure after t equals 5. So I'm just gonna plug in 5 for t. And let's put that in the calculator. So 30 times 0.9 to the power 5. What do you suspect? It's going to be a decay, right? Because it's leaking. So if I multiply by a number less than 1, it's going to mean decay. So after 5 minutes, the tire pressure will be 17.71. I believe PSI. This is measured in PSI. So this is 30 initial PSI, 17 PSI. Give the decay factor and explain what it means in context. So the decay factor is 0.9. Okay, so what does it mean in context? With each minute, the tire pressure is multiplied by 0.9. Okay. Next, let's determine which of the following are exponential, and then for each exponential, identify the growth or decay factor and the y-intercept. Alright, so let's look at the first one. This is exponential. So x is the exponent, so this is going to be exponential. X is the exponent, this is also exponential. This is also exponential. This is also exponential. This one is not exponential because x is not the exponent. Okay? So let's write down C, it will be 20 in its growth with growth factor 1.04. For this one, C is going to be the initial amount, so it's going to be actually 20 plus 1.04 to the 0 power, right? So this is 20 plus 1, which is 21. And then the growth factor is also 1.04. For the next one, C is 5, and then the growth factor is 3. For this one, C is 1, because I don't have anything in front of the 4, which means it's 1. And then the growth factor is 4, so it means it quadruples. Okay. The graphs of exponential functions are going to look very similar. It only depending on if it's an exponential growth or exponential decay. So you notice that this one is exponential growth. The function is increasing. And then, so this is for when a is greater than 1, when we have growth. And this one is for a is between 0 and 1. This is decay. The function is decreasing with time. Notice that there is a horizontal asymptote, which is the x-axis at x equals 0, right, for both of them. So this means that the graph gets really close to the x-axis but never quite reaches it. So there is no x-intercept in here. Notice that the domain is all real numbers, but the range is only values greater than 0. You see how we don't have graph below the x-axis. So the range is only from 0 to infinity, not including 0 because we don't have an x-intercept. Now what is the end behavior? As x goes to infinity, so as x grows really large, I see infinity in here, notice that the graph goes up to infinity. And as x grows, well, it doesn't grow, as x goes to negative infinity, you notice that the graph approaches the 0 value. Okay, so we say as x goes to infinity, the function approaches infinity, and as x goes to negative infinity, the function approaches 0. For the decay function, it's reversed. As x goes to negative infinity, the function goes to positive infinity. And as x goes to 0, as x goes to infinity, the function goes to 0. It's very important to distinguish between linear function and exponential function. So let's see how are they different and how are they similar. For example, if you're given the function f of x equals 100 times x to the 50, and the function g of x equals 100 times 2 to the x, which one is exponential? The one that has x, the unknown, as the exponent. This one is not exponential. This is a power function. We learned about these earlier. But what we want to emphasize in here is that in the long run, eventually, the exponential function will dominate, will have larger outputs than f of x. Because exponential functions represent situations where a value is being multiplied by a constant repeatedly. Linear functions represent situations where a value is being added to by a constant repeatedly. So for example, if you're looking at a flock of geese that starts with 10 geese at time 0, and if the flock increases by 4 geese per year, the formula will be, well, you start with 10, and with each year you add 4, so it will be 4 times t. So this is linear, because you're adding a constant repeatedly. So linear means I'm adding 4 repeatedly. Now, if the size of the flock increases by a factor of 1.4 each year, this means, we're going to call this one g of t. So it means you start with 10, increases by a factor of 1.4, means it's multiplied by 1.4 each year. So this is going to be exponential. So exponential functions represent situation where a value is being multiplied by a constant repeatedly. So this is multiplied by a constant repeatedly. This one, a constant is added. In this case, the slope is added repeatedly. So it's added opposed to multiplied. To graph each of the model on the same coordinate system, let's use our calculator. So we're going to go to our graphing, y equals, let me clear. So I'm going to graph the linear, so it'll be 10 plus 4x, and then the exponential 10 times 1.4 to the power of x. Let's pick a good window. So the input time, so it can be negative, so let's start at 0, and let's look over a period of 20 years. I know that I'm starting with 10 geese, so let's go up to, I don't know, 500, we'll try, and then we'll go in increments of 1. So let's graph. This is the linear function, and then the exponential. Let's actually reduce our y window so that we can see better. Let's go to 50. So this is the linear, and see the exponential. Do you see how the exponential is going to be larger immediately after 2 years? You see how much more higher the y values are for the exponential than the linear function. Okay? So exponential functions dominate all the other functions. So in the long run, the exponential is going to have larger y values, larger outputs than any other function. All right, so let's determine whether each table represents linear growth or exponential growth.